My name is Isaac Tigani, and I'm from Mepham High School in Belmore, New York. I worked on a research project involving discriminating between radio signals reflected by airborne phenomena. I worked with Mr. William Leacock, my physics teacher at Mepham High School, and Dr. Helio Takai, a physicist at Brookhaven National Labs.
The purpose of this project was to create a viable system for analyzing data being recorded by the MARIACHI radar system, which can now detect airplanes, meteors, lightning events, and hopefully someday cosmic rays. I wanted to create an algorithm which could both detect and sort these signals automatically. What you're looking at right now is a real-time stream of radar data in the form of a waterfall diagram. This is simply a visual representation of the amplitude and frequency of the radio signals shown as a function of time. The raw data seems complex, but when contemplating how to sort through such feeds, I realized how easy it was to recognize a signal just by looking at it. This gave me the idea to use image recognition, and so I set off to record data and begin experimentation.
This is the inverted V-type dipole antenna that I built for my project. It consists of 4 aerials, each of which are a quarter wavelength of what we're trying to pick up, and a pair of these aerials makes up a half wavelength. The copper elements are supported by a PVC spider support system, and the main stem of the antenna is also PVC. Here you see the base, which was originally supposed to be a Christmas tree stand, but it's more difficult than you'd think to find a Christmas tree stand in July. What you see here on the inside of the antenna is the wiring. Aerials located across from each other are connected to each other via coaxial cables, and these cables are then streamed through RF chokes, which isolate the aerials from the wires connecting the antenna to the BNC connectors. These BNC connectors are then attached to an additional coaxial cable, which brings the signal to a hardware receiver connected to a computer. This is the coaxial cable from the antenna outside. It streams the radio data from the antenna into this receiver, which then converts it into a digital serial signal. That serial signal is picked up by the sound card in this computer. The sound card will convert that signal into a wave signal, which can then be read by software on the computer.
This is the software that controls the hardware receiver. It allows them to turn on the antenna as well as tune into specific frequencies. This is an example screenshot, which is a snapshot of about 5 minutes of radar data. This is what my algorithm uses as a data source. This image is first converted to grayscale so that edges can be mapped out. Edges are data vectors which point to junctions of pixels with particularly drastic changes in brightness. The intensity of these changes is known as edge strength. Once edges are mapped out in a diagram, they are extended and approximated to form closed shapes or contours. This data is further simplified by fitting ellipses to each contour that satisfies certain minimum requirements for size and edge strength. This is the code that looks at the axes of the ellipses, which represent the time and frequency spans of signals, which can be used to distinguish them. This is the program in action. Screenshots are loaded and analyzed. While only one is shown here, the software has batch processing capabilities which can process months of data in just a few short hours. Airplanes are represented by red ellipses, small meteors by gray ellipses, and large meteors by green ellipses. Just a small mid-range frequency band is being analyzed. This is why the airplanes towards the bottom half of the waterfall diagram aren't being picked up. This and all other thresholds are completely controllable. While more needs to be done to improve the accuracy of the algorithm, and profiles for new signals must be identified, it's a good step in the direction of one day being able to detect cosmic rays via radar.